Okay, in the first lecture we have determined the total number of microstates for different configurations such as NS, N, NP, N, ND, N, NF, N, EG type of configuration and T2G type of configuration. Sometimes we also have to obtain the total number of microstates for 2S1, 2P2 type of configuration. So for this we have already determined microstates for S1 configuration, which is 2, and we also have calculated the total number of microstates for P2 configuration, and which were 15. So for this configuration total number of microstates would be 30. So for obtaining total number of microstates for this configuration, we have to use the combined n factorial equation, one for S1 configuration and second for P2 configuration. So for S1 configuration, the n factorial equation will be 2 factorial by 1 factorial into 2 minus 1, that is 1 factorial, into n factorial equation for P2 configuration, and for P2 configuration the equation is 6 factorial by 2 factorial into n minus n, that is capital N minus small n, that is 6 minus 2, that is 4 factorial. So by solving this equation, here we will get 2 into 1 by 1 into 1 into 6 factorial can be converted into 6 into 5 into 4 factorial, and 2 into 1 into 4 factorial. So 4 will get cancelled. 2 6 by 2, that will be 3. So the final answer is 2 into 15, that is 30. So for NS1 NP2 configuration, the total number of microstates we have calculated, that is 30. So with this, here we will stop for calculating the total number of microstates, and now we will proceed towards obtaining or constructing the microstate table. So first we will take as an example the determination of term wave functions, that is microstate table for ND2 configuration, D2 configuration. And here we will take the example as vanadium 3 plus free metal ion, for which the electronic configuration is 3D2. In the point of microstates, we have obtained total number of microstates for D2 configuration, which was equal to 45. So we have to show these 45 combinations of electrons with different ms, that is spin quantum number, and ml, that is different orbital quantum number. So for this, first we will obtain the total orbital quantum number for this configuration, and then we will obtain total spin quantum number for this configuration. So total orbital quantum number can be obtained as it is summation of MLI, where ML is the orbital quantum number of individual electron. So I is the number of electrons. As there are 2 electrons, we can obtain total ml as ml of first electron and ml of second electron. Now we know there are 5 d orbitals having 5 ml values, as first ml is plus 2, second plus 1, 0, minus 1 and minus 2. So these 2 electrons can have, or each electron in the d orbital can have the ml value of plus 2, plus 1, 0, -1 or -2. Means this first electron can be placed in any one of these 5 orbitals. Similarly, the second electron can also be placed in any of these 5 orbitals. So second electron can also have the ml values of +2, +1, 0, -1 and -2. So the highest ml value, total ml value, possible ml value, highest value possible is 2 + 2, that is +4, and lowest ml value possible is -4, and middle all values are possible because we can place one electron in ml +2, second electron in ml +1, so +3 value is also possible. Similarly, we can place one electron in -2 and other electron in -1, so it is possible that is +3. So the range of ml, total ml values, total orbital quantum number values, it is from +4 to -4. The next we'll determine total ms value. As there are 2 electrons, the total ms can be calculated as ms can be calculated. It is given by summation of msi. Again, this small ms is the spin quantum number of individual electrons. So, as there are 2 electrons, ms1 spin quantum number of first electron plus the spin quantum number of second electron. We know that the electron can have only 2 spin values, that is either +1/2 or -1/2. So, the first electron can have the spin values of +1/2 as well as -1/2. Similarly, the second electron can also have both the spin values, either +1/2 or -1/2. So, when both the electrons have +1/2 spin values, total spin will 1, and when both the electrons have -1/2 spins, the total spin quantum number will be -1. The one electron may have +1/2 and other may have -1/2, or the first may have -1/2 and other may have +1/2. In both these cases, the total spin comes to be 0. So, the total ms values here available or possible are 1, 0 and -1. By using these total spin quantum number and total angular orbital quantum number values, we can construct the microstate table, or we can obtain the number of microstates, and we can also assign these microstates to different terms or Russell-Saunders terms. So next we see the construction of microstate table, for D2 configuration, and also the nomenclature of terms. Or it is also, we can also call as assignment of microstates to terms. So here, for microstate table, we can use the total ms and total ml values, and in the table prepare a table. The first column is for total orbital quantum number, and this line, it is for total spin quantum number. So here write down ms and here write down ml values. Now the total ms values we have obtained are 3, that is 1, 0 and -1. So Under these three total spin values, we will obtain different microstates, and there are plus 4 to minus 4 ml values. So plus 4, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3 and minus 4. So first we will show the microstate for Ml4 and Ms1. Means here we are going to represent two electrons with respect to their spin values and orbital quantum number values. So in order to get the total orbital quantum number 4, we have to place both the electrons in this first orbital having Ml value of plus 2, and in order to get total spin of 1, we have to place both the electrons in this same orbital, both having the plus 1/2 spin. But according to Pauli's exclusion principle, this arrangement of two electrons in the same orbital is disallowed. It is not allowed because the two electrons cannot have all the four quantum number same values. So we will not get microstate under this at this place, which will have total Ml plus 4 and Ms plus 1. But here next we'll see under this column total spin 0 and Ml4. Here it is possible that both the electrons can be placed in this orbital, one with upspin and other with downspin. And this arrangement is possible because this second electron has 4 quantum number value different, that is Ms is minus 1/2 first electron, Ms is plus 1/2. Otherwise these two electrons are having 3 quantum numbers same value, but they differ in the 4th quantum number, that is Ms value. So this arrangement or this pair of electrons can be represented in a simple bracket. At the base, the orbital quantum number of first electron, that is 2, and the orbital quantum number of second electron, again it is 2. At the base, the orbital quantum numbers are shown of the two electrons, and on their heads the spin values are shown of these two electrons. The spin of first electron is plus 1/2, therefore only plus sign is placed on the head, and the spin of second electron is minus 1/2, so only minus sign is placed on the head of the orbital quantum number of second electron. So you can see now the total orbital quantum number 2 plus 2 becomes 4, and total spin plus minus becomes 0. So here we get only one microstate. Such combination is not possible by any other arrangement. Now one rule is that if we are not getting the microstate under Ms1 and Ml4, then we also don't get microstate under -1 and +4, because in the same manner we cannot place two electrons in this Ml value with both having -1/2 spins. Next, in this +3, Ml +3 and different spin values, now it is possible total orbital quantum number of both electrons should come +3 and total spin should come 1. So for this we can place one electron in +2, and it is possible to place other electron in +1, both having +1/2 spins. So the total orbital quantum number becomes 2 plus 1, that is 3, and total spin becomes +1/2 and +1/2, that is 1. So this microstate we can show as first electron orbital quantum number 2, and second electron orbital quantum number 1 and their spins are plus plus. Once we get here, the same arrangement is possible for the minus 2 and plus 2 having both spins up. So, for this arrangement, we will get the microstate, that is 2, minus 2 and minus 1. So, total, here it is 2 and 1, total spin minus 1. So, both electrons can have this, this arrangement is in the minus 3 ml value. So, both the electrons can be placed in this way, in these two orbitals. So, the now ml value remains same, but the total spin becomes minus 1. So, this microstate can be shown as 2, 1, but both spins are minus. Now, from this microstate, we can get 2 more microstates, but the total spins are different. So, we can arrange these 2 electrons, one with plus 1/2 spin and other with minus 1/2 spin, and this microstate can be shown as 2, 1 and spins plus and minus, and second microstate is also possible, that is now this electron will have minus spin and this electron will have plus spin, and this microstate is shown as again 2, 1, minus and plus. So, once you get this microstate, you can easily obtain these 3 microstates just by changing the spin signs. Then for plus 2 ml value, for these 2 electrons, total ml should be plus 2 and total ms should be plus 1. So the possible arrangements are, here we have to decrease ml by 1 unit. So it is possible that first electron will be in plus 2 and second electron will be in 0. Similarly, it is also possible to show this arrangement in 1 and in 0. So, plus and plus we are getting 0. Then there is no other possibility for getting the plus 2 ml and plus 1 ms. So, only one microstate we are getting here. From this microstate, we will obtain the minus 1/2 microstate, that is 2, 0, 2, 0, but spins are now down spins or negative, and from this microstate, here also we will get 2 microstates, that is 2, 0. In the first microstate, first electron will have plus 1/2 spin, second electron will have minus 1/2 spin, and in the next microstate, the first electron will have minus spin value and second electron will have plus spin value. The one more microstate here we will get, because the total spin is 0, and that is by placing both the electrons in plus 1 ml value, one with up spin and other with down spin, because for this first electron ml is 1, for second electron ml is 1. So this microstate can be shown for first electron ml1 and for second electron ml is 1, and first electron has spin plus and second electron has spin minus. So total spin comes to be 0 and total ml comes to be 1. Next we will obtain the microstates for plus 1 ml and 1 ms. Here from this we can proceed to the obtaining microstate. So here further we have to decrease the ml value by 1 unit. So we can write down here the first electron in plus 2 ml and second electron in minus 1 ml. 2 minus 1, that is 2 and minus 1. So total ml comes to be 1, and spins both can have plus plus, that is total spin becomes 1. There is one more possibility for arranging 2 electrons to get the total ml1 and total ms1, that is 1 electron in plus 1 value and other electron in 0 value. So the second microstate is 1, 0 and both have half spins. So total ms1 and total ml1. Now from these 2 microstates, here you have to write down 2 microstates by changing only spin values and keeping the ml values as it is. So 2 minus 1 and 1, 0, but now the spins are minus, so that total spin becomes minus 1. From these 2, here we will get total 4 microstates, and these 4 by interchanging the spin signs of these microstates. So from these 2 microstates are possible, that is 2 minus 1 and 2 minus 1, 2 in dot minus 1, and for these 1, 0 and 1, 0, only you have to interchange the spin values. For this first electron plus spin, second electron minus spin. Now first electron minus spin, second electron plus spin. For this also first electron plus, second minus, and first minus and second plus. Again here, so in this way, for plus 1 ml value, we have totally 1, 2, 3, 4, 5, 6, 7, 8, and one more arrangement is possible for total ml, only 4 arrangements. Then next we will see the 0 ml and 1, 0 and minus 1 ms values. So for 0 ml, now in this way we have to keep the decreasing order of ml value. So if the first electron is plus 2 ml, second electron should be in minus 2 ml. So total ml would come to be 0, and both the electrons will have plus spins. Similarly, for getting total ms1, the 2 electrons can be placed in one in plus 1 ml and second in minus 1 ml. So that is plus 1 and minus 1. This is for second microstate, and plus 2 and minus 2. This is for first microstate, and in both cases the spins are plus 1 half. So total spin comes to be plus 1 and total ml comes to be 0. Now from these 2 you can prepare here 2 microstates just by changing the signs of spins. 2, minus 2, 1, minus 1, both minus spins, minus 1 half spins. So total spin comes to be minus 1. Now from these 2, here you will get 4 microstates. 2, minus 2, 2, minus 2, 1, minus 1, 1, minus 1, and now just you have to interchange the spin signs. First plus, minus, then minus, plus, plus, minus, then minus and plus. So here also we are getting total 8 microstates, and one more possibility in this middle column is there, that is we can also obtain 0 ml and 0 ms by placing both the electrons in ml0 orbital. So this microstate can be shown as 0, both the electrons in 0, so ml values for both the electrons are 0, but the spins are opposite, first plus and second minus. In this way we have obtained total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 microstates for plus 4 to plus 1 ml values, and same 18 microstates for minus 4 to minus 1 ml values. So 18 plus 18, 46, 46, 47, 36, 36, 37, 38, 39, 40, 41, 42, 43, 44 and 45. So total 45 microstates are possible. So how to get the microstates for minus ml values? So for getting minus ml microstates, just I will explain for minus 1. Now these spins are going to be same, total spins are going to be same, only total ml is changing, that is from plus 1 to minus 1. So how to get? If once you have obtained the microstates for plus 1, it is very easy to obtain the microstates for minus 1 ml. Just you have to change the signs of orbital quantum number of these two electrons. So see here, the first microstate under ml plus 1 and ms1 is 2 minus 1. So under this minus 1, you have to change the signs of these two. So plus 2 will become minus 2 and minus 1 will become plus 1, and these spin signs are same. Second microstate you will get like plus 1 will become minus 1 and 0 it will remain as it is, and both have same spins. So in going from plus 1 to minus 1, just you have to change the signs of orbital quantum numbers of individual electrons, and while going for ms from 1 to minus 1, you have to change the signs of spin values or spin quantum numbers. So in this way, for this under this plus 1, minus 1, here also the minus 2, 1 and minus minus and minus 1, 0, both minus minus. Similarly here, these 4 you will get here, that is 2, minus 2, plus 1, minus 2, plus 1, the same orbital quantum numbers, minus 1, 0 and minus 1, 0, and the same spin values, that is plus, minus, minus, plus, plus, minus and minus, plus. In this way, for remaining ml values also you may prepare the microstate table and complete. Actually, it is not necessary to write down the microstates for minus, minus 2, minus 3, minus 4 once you get the microstates up to 0, because only ml signs and ms signs will change, otherwise the total values will remain same. So this is about the 45 microstates. Next we will see nomenclature of microstates. Nomenclature of microstates or assignment of microstates to different arrays terms. So we'll begin with the first microstate, that is 2, 2 plus minus. So for this microstate, the total ml is 4 and total ms is 0. So here we have seen that the turn symbol depends upon the L value. Turn symbol depends upon total orbital quantum number value. So, and we have also seen that when L is 0, the turn symbol is S. When L is 1, the turn symbol is P. When L is 2, turn symbol is D. When L is 3, turn symbol is F, and when L is 4, turn symbol is G. So, as the total L value is 4, the turn symbol for this microstate means this microstate is belonging to the array's term G. And for this term, spin multiplicity, total spin multiplicity is nothing but it is 2s plus 1. And for this state, total spin plus minus, so total spin is 0. So total spin, that is s is 0. So 2 into 0 plus 1 is equal to 1. So spin multiplicity of this term is 1, that is singlet. So first we get the singlet G term. As the total spin is 0, means the term is singlet, all the microstates belonging to this array's term will have only one spin value, and that is 0. But the orbital multiplicity, so this is about spin multiplicity 1. For G term, orbital multiplicity, for G term, orbital degeneracy or multiplicity, it is equal to, it is given by twice L plus 1. So L value for G term is 4. So 2 into 4 plus 1 is equal to 9. So orbital multiplicity is 9, and this orbital multiplicity, it covers the ml values from plus 4 to minus 4. So as the orbital multiplicity is 9, there will be 9 microstates belonging to this term G under the single spin value, that is S, and those will be in plus 4 to minus 4 ml values. So we have to allot one microstate from each ml value under the 0 spin value to the singlet G. So here singlet G, this term belongs to singlet G, this term also belongs to singlet G. Out of these 4, one term belongs to singlet G. Among these 4, one term we have to allot for singlet G, and here also one for singlet G. Likewise, from the minus 2, minus 3 and minus 4, one microstate each under this singlet G term. Then we'll come to the next microstate for nomenclature, and the next microstate is this one. For this microstate, L value is 3, and just now we have seen that when L is 3, the turn symbol is F. Turn symbol is F. Now for this microstate, the total spin is 1. Total spin is 1. So spin multiplicity of this microstate will be 2 into 1 plus 1, that is 3. So spin multiplicity, that is spin multiplicity of F term is 3. It means spin multiplicity 3 means the 3 spin values are possible, and these 3 spin values are 1, 0 and minus 1. So the microstates belonging to triplet F term will be present under all the spin values, and for plus 3 to minus 3 ml values, because the spin degeneracy, orbital degeneracy of F term, for F term L is equal to 3. So orbital degeneracy of F term is equal to twice L plus 1. So 2 into 3 plus 1, that is 7. Orbital degeneracy is 7, means the microstates belonging to triplet F will be present in all the ml values from +3 to -3, and as the spin multiplicity is 3, these microstates will also present in all the 3 ms. So first triplet F, here this microstate will belong to triplet F, this microstate will belong to triplet F, triplet F, triplet F, triplet F. First we will go to triplet F, then here second we will go to triplet F, triplet F. First we have to allot to triplet F in this column, second we will go to triplet F, triplet F, and likewise for the remaining ml values, triplet F. In the same way, triplet F here, 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 here and here. Now, next term for nomenclature, it is, we have covered this, next term is this one. So, we have to classify this term. For this term, ml value is 2, therefore term symbol for this microstate is D, and as the total spin is 0, this is singlet D. So, singlet D. It means microstates belonging to singlet D will be present only in one spin value, under only one spin value, that is 0, and as the orbital multiplicity of D, for D term L, total orbital quantum number value is 2, therefore total or orbital multiplicity or orbital degeneracy of the D term is twice L plus 1, that is 2 into 2 plus 1 means 5. Means it will cover the 5 ml values from +2 to -2. So singlet D under 0 spin and ml values +2 to -2, there will be 5 microstates. So singlet D, here third will go to singlet D, here third will go to singlet D, and here also third D will go to singlet D, and here singlet D. So total 1, 2, 3, 4 and 5. Then next term which is to be classified, it comes to be this one. So for this term ml value, total orbital quantum number is 1, and when the L value is 1, the term symbol is P, and the total spin is 1. So again 2s plus 1, that is spin multiplicity is 2 into 1, total spin here it is 1, 2 into 1 plus 1 twice 2s plus 1, s is total spin is 1, so 2 into 1 plus 1 is equal to 3. So the spin multiplicity of this term is 3. 3 spin multiplicity means the P term will be present in the 3 spin values, under the 3 spin values, and as the orbital multiplicity of P term, for P term L is equal to 1. So orbital multiplicity twice L plus 1, twice L plus 1 is equal to 2 into 1 plus 1 is equal to 3. So this P term will cover 3 ml values from +1 to -1. Therefore we can assign triplet P, this is assigned to singlet D, so it will be triplet P, this will be triplet P, next triplet P, next here fourth will belong to triplet P, here second will belong to triplet P, and for -1 this is triplet P, this is triplet P, and this is triplet P. So total 9 terms, 9 microstates will be under triplet P, that is 1, 2, 3, 4, 5, 6 and 7, 8, 9. And the next term which is remaining classification is this one. For this term L value is 0 and when L value is 0, turn symbol is S, capital S. And as the total spin for this microstate plus minus, that is 0, the spin multiplicity is 1, that is singlet. And for this singlet S term, this term will be present under the single spin value, that is 0, and for this S term L is equal to 0. L is equal to 0. So orbital multiplicity of S term is twice L plus 1, that is 2 into 0 plus 1 is equal to 1. So this term will present only at the ml value of 0, that is single ml value, and ms of 0. So only one microstate is belonging to singlet S term. So in this way, for D2 configuration, we are getting 45 microstates, all these representations, and total RS terms, which are Russell-Saunders terms obtained for D2 configuration are singlet G, then triplet F, then singlet D, then triplet P and singlet S. So in this way, 5 RS terms are obtained from this microstate table for D2 configuration. So in this way, you can obtain the total number of microstates, and you can also build up the microstate table for the given configuration, and you can find out the possible RS terms, that is energy levels, for the free metal ion or for the given configuration of free metal ion. So with this we will stop here.